Hey guys, what's going on? So today we're going to be covering the Riemann Curvature Tensor. This is going to be the big boy in GR because we're going to derive so much from the Riemann Curvature Tensor, so we're going to spend quite a bit of time on this guy. We're going to derive the Ricci Tensor after this using Riemann Curvature. We're going to derive Ricci Scalar and so many other different types of invariant scalars such as the Kretschmann scalar, the Euler scalar, and so much more. We're going to be able to understand all these scalars in terms of the Riemann scalar and hopefully also in terms of everything that we've been using to build up the Riemann tensor, right? So this is sort of where GR really kicks off its advanced feat, if you will. And then from there on out, this is going to be fairly advanced stuff, hopefully advanced enough for you to be proud in what you're understanding, but also not super advanced enough so that you can understand. So let's get right into the material. Make sure to hit that like and subscribe button, and make sure to go into my Patreon page if you want to support the channel, and also if you want to get summary sheets as well and notes. So let's get into the topic. So we are talking about the Riemann Curvature Tensor today. What we're going to be going over, or the idea of what the Riemann Curvature Tensor is supposed to be, is suppose we have some manifold, okay? And suppose on this manifold we can walk in multiple directions. So suppose we're starting here. Our mantra here has always been, okay, we're living on some manifold. We're standing at some point on that manifold. The idea with the Riemann Curvature Tensor is, okay, we have this idea of a metric, okay? The Riemann Curvature Tensor is really going to tell us what happens to this metric, or what happens to a vector at this space that we're measuring, right? So what happens to the vector at some unit length that we're measuring at this point in space and time, if we were to say travel in one direction along the manifold and then in another direction along the manifold, okay? And how does that different from if we were to travel in this direction first and then in this direction to get to the exact same point? If the two are different, then this is a litmus test for the manifold being curved, and this is going to get into ideas of parallel transport as well. But really what we want to do is we want to take the derivative of the vector, this vector here, as we first travel in this direction. So this direction is going to be the x1 direction, and then in the x2 direction. And then we're going to put that in the back of our mind, and then we're going to do this in the x2 direction and the x1 direction, and then we're going to compare the two. So we're comparing both paths. We're comparing this path to this path, and if the comparison yields a non-zero result, then this is how we're going to define curvature, okay? We'll later get into ideas of parallel transport and how parallel transport is all related to this as well. Anyways, let's get started. So we started to talk about the covariant derivative in earlier videos. The covariant derivative, again, is this idea of the derivative of some vector in the x1 direction, okay? And this is a basis vector. These are the components of the basis vector. And this comes from that realization, right? So this is the covariant derivative of v in the one direction, okay? And this isn't new stuff, right? There's tons of videos on YouTube that cover this, okay? And so this is going to be somewhat of a video that's not unique to videos out there already on the Riemann Curvature Tensor. What's going to be unique is how we're going to go from the Riemann Curvature Tensor to other important ideas in GR, and that's what's going to make this unique. So this is sort of, again, the jumping off point. Okay, so we go from here to here just by moving the product, okay? And after moving the product, we can then take the derivative of this, which is right here. This is product rule here. So what I'll do is every step I do, I'll say, okay, this is product rule, and then from here to here is defining the Christoffel symbol, right? So that's this guy and this guy. That's that definition. All right. And then from here to here, we are really just moving things around. So we'll say rearrange, right? So we're just bringing this guy over here. Okay. And that's how we get to this point right here. This is a 1-1 tensor, right? Because 1-1 tensor. So that means that these are the components to that tensor. So we encapsulate all this information into this object right here. This is the covariant derivative of the vector, right? And so we have 1 summing over 1 and alpha summing over alpha. So this is a 1-1 tensor. All right. So we can now take the second covariant derivative of a vector. So the same thing, right? So this green block here, we're going to do the same thing. It's just a little bit more complicated because now we've done this. We want to do this a second time. And this corresponds to, so we went in the one direction. We're doing this yellow path first. We went in the one direction. Now we're going in the two direction. And we have this, right? So this is taking that second derivative of our vector, okay? Or of our 1-1 tensor. So again, we move the product. So moving the product. And then to get from here is the product rule. All right, and then from the product rule, we can see we are defining again our Christoffel symbols. So you could sort of see a pattern here. We have product rule, define Christoffel symbols. Product rule, define Christoffel symbols. Okay, so Christoffel symbols have to sum over a dummy index, and then this Christoffel symbol here, we're summing over a dummy index as well. All right, and the reason this is a negative is because the Christoffel symbol is negative when we are taking the derivative of a vector as opposed to a covector. Right? So if it was a covector, the sign is just opposite between vectors and covectors. And I don't think I've derived that yet. I'm just saying it right now. I'll derive it later in a different, maybe in a different video. We really want to get to this point where these videos are going to be unique to this channel, right? And so I've sort of rushed us to the point of coming to the Riemann Curvature Tensor. However, you can also go back in my tensor calculus playlist and see a lot of these derivations in detail already. Okay, so this channel somewhat builds on that playlist, or this playlist somewhat builds on that playlist. I want to keep these relatively self-contained though, so if there is something that I allude to in my tensor calculus playlist, you can go ahead, watch that over there, and then come back to this playlist. But anyways, so here is, okay, so we go from here, so now we go from here to here by renaming dummy indices, right? So we rename these dummy indices, right here, I'll erase some of this. So we can make this a 1, so we make mu's 1s, all right, and this is a dummy index, so we can change those dummy indices, all right. And again, dummy index, we're changing alpha. So here, changing mu's to alphas. So we have to do the same here. Here, they're summing over the dummy index again because we want this E1 right here. So we want this E1 right here, because what we'll be able to do now is, now that we have E1, and I'll just erase just to clean a few things up. Here's our E1. We also have E2 and E2 and E2, and we also have E alpha, E alpha, and E alpha. So there's our alphas, there's our E2s, and our E1. We're taking all of those out, and we now have the formula for the components of this double derivative. All right. So once we get the components of the double derivative, now we have, so we can actually flesh this, we can flesh all of it out to get this right here. So to go from here to here, we're just taking derivatives. So taking the covariant derivative. All right, so we're taking covariant derivative here to get this, covariant derivative here to get this, and here to get this. So this is, this guy right here is the full-on double derivative of some vector first in the one direction and then in the y direction. So in the x direction, in the y direction. Right, we just have to fill it. So 2, these just have to match, right? So 2, 1, 1, 2, and then 2, 1, 1, and then 2, 1, and alpha. So this can be a little bit daunting. Typically, you're not really required to memorize this. But what we're going to do is we're going to take this now, and here it is. This is the double derivative of the vector. Now we're going to go in the other direction, right? So we're going to go, so we went in this direction. Let's go in this direction now. So when we go in that direction, I'll just write it out, right? Because all you have to do is wherever you see a 1, you replace with a 2. So in this one, we had a 1 here, so we put a 2 here, put a 1 here. And you can go through all of that. And what you'll find is that if you subtract the 2 from each other, these two guys are going to cancel, these guys are going to cancel, this and this will cancel, this and this, this and this. So all the things that cancel are canceled in their corresponding colors, which is what I did here. And again, all of this can be found in the summary notes. And then we get this minus this, which is right here. These are the components of that. This should be a 1. Right, so that should be a 1. And this here, so now we get to this point. So how do we get to this point is we're just, we got a pen going, changing the name of dummy indices, right? Changing dummy indice names. So we're changing gammas to mu's, mu's to gammas, gamma to mu, mu to gamma, and then we just, these are all dummy indices, so we can keep those as well. So again, we're just dummy indices, all right? And then to get from here to here, we're just taking out v mu. Okay, so now that we've been able to have everything, now that we have v mu everywhere, so we went from v gamma v mu up here to v mu. Now we're able to take v mu out. Right, and we have v mu's over here as well. All right, so I'll just erase all this. I want to keep this as a 1. That was a mistake when I was typing this. And so now we have this guy. So what is this? So this is the tensor. This is the Riemann Curvature Tensor. This guy right here. This Riemann Curvature Tensor, the way we calculate its components are with this. And that's what I have right here. So this is how we calculate the Riemann Curvature Tensor. It's in terms of the connection, derivatives of the connection, and the connections themselves. There's going to be a lot of summation over dummy indices in this, but the point is that the Riemann Curvature Tensor can be calculated just through our components, or just to our connection. Our connection, it can be in terms of the metric, so everything really comes down to the metric tensor. Okay, but this is how we compute the coefficients of the Riemann curvature tensor, which represents the difference between the two paths that we take on the manifold. And when we let's take a look at that now in this picture. So we took a look at the two paths. This green path was in the one direction first, and then two direction. Right, so I have the one direction in orange and orange. Let's see if I have an orange color here. Here's some orange in the one direction. That's in the one direction. And then let's see if I have a blue color in the two direction and in the two direction. So in the green case, we're doing one first. We're doing one first and then two. Right, so 1 and 2, and then 2. In the brown case, we're doing 2 first, so 2 first, and then 1, and then 1. So the difference between these two paths, if there is a difference, right, if there is a difference, then R alpha mu, actually I want to do it like this, alpha beta, here, I'll do this in black actually, let's do this in black. So R alpha beta mu nu. This guy is going to not be 0 if the two paths are different or yield different results. Okay, and this is how we're going to define curvature. This is how we're going to define what it means to be curved on a manifold, and this is also going to help us in understanding parallel transport as well. There's a few things I want to talk about the Riemann curvature tensor as well, and we'll get more into this as we talk more about contracting the Riemann curvature tensor and all that really fun stuff with developing the Ricci tensor and the Riemann scalar. But let's take a crack at just introducing these concepts before we dive deep into them. So I have a blank whiteboard here. The idea is Riemann curvature tensor alpha, beta, nu, gamma. If alpha and nu are the same, so if alpha equals nu, then we're going to get R mu, beta mu, nu. And this is R beta nu. And this is the Ricci tensor. And we're going to see what the geometric understanding of this guy is. And it's going to be quite interesting to see how we go from this idea of, we can sort of almost think of it as like a closed path on the manifold, right? So we go from this idea of, here I'll rewrite this, R beta nu. This guy here talked about, so we're talking about closed path on a manifold, right? So here I'll draw this a little bit better. Talking about a closed path on a manifold. All right, so here's our manifold, and we go in one direction and the other direction, and then we go in this direction and this direction. So this picture is the picture we want to keep in mind when we're talking about the Riemann curvature tensor. When we talk about the Ricci curvature tensor, the picture we're going to want to keep in mind are spheres evolving into other spheres on a manifold. Okay. This has to do with volume changes, right? So suppose you are standing here, this is point P, and this is going to be point P as well. The two things are telling us something different, though. One is telling us how these two guys are closed. Okay, and I'm going to undo that. I'm going to do a different color. How these two paths are closed. Okay. The Ricci tensor is going to tell us something about volumes. So the volume of some sphere at point P. What's the volume going to do at some other point if we travel some other direction on the manifold? So say we travel this direction on the manifold. And one way to think of this is, suppose we have our manifold, and suppose on that so the manifold's curved, okay, and we're standing here at point P. Well, point P is, we can imagine some circle here. And if we were to travel, say in this direction, this, or not circle, say this sphere on the manifold gets bigger. All right. So that would be this path right here, like this path that we're traveling around or on, okay? And so this is going to tell us something about how spheres, how the volume of spheres change as we traverse ourselves along the manifold. And this is a volume, right? So this tells us something about a volume. If we contract this more, we can say, right, we can actually contract this more, and we could say, well, the Riemann Curvature Tensor, this is the Ricci tensor. The Ricci Scalar, well, this is just going to be R. And we can contract that. R is equal to R beta nu, R beta nu. This guy here is going to tell us something about how areas, right? So how the area of some sphere deviates from, actually I'll draw it like this. Suppose we have a sphere. We're standing at point P on the sphere. Here, oops. We're standing at point P on the sphere. And we have, so here's our sphere. Suppose at point P, we're standing right here at this point. Well, this area here, this is a curve. Since this is a curve, it's going to deviate from the area if it was flat. So here's point P. This area here, that's point P. What the Ricci scalar is going to tell us is how much this area deviates from flatness if we're standing at some point. So there's three things that we can sort of take note of at every point in space, right? Those three things are this here, so closure, right? So that's going to be Riemann. Okay, then there's going to be volumes. That's going to be Ricci scalar. And then there's going to be areas. And that's going to be explained to us by the Ricci. That's going to be the Ricci scalar, right? This is going to be the Ricci tensor. This is a tensor. And this is a scalar. Okay, so at every point in space and time, we can we can calculate these guys. Okay, and these guys right here are going to be super, super important for determining future invariants, right? Because the idea here is now going to be, well, this is a scalar. This is an invariant. This is a scalar field. Scalar fields are invariant regardless of how you transform them. Okay, are there other invariant scalars that we can develop? And there indeed are, right? So I mentioned the Riemann scalar. Let's see if I can spell this right. I think it's SCHMANN scalar. And then there's going to be the Euler scalar. There's also going to be the Chern. Can't remember. There's a second name there, but I'll just call it the Chern scalar for right now. But these scalars also are going to tell us something about how things are going to change on this manifold. I don't really want to give it away right now, but we have these scalars, right? This 2, 3, and 4, and we're going to go over these guys in some depth, and then we're going to move on to talking about some actual examples. The Schwarzschild example, the Kerr-Newman example, the Kerr example, the Reissner example. These all have to do with describing black holes. Because this is a playlist on physics and not just strict mathematics, we are going to really get into that kind of stuff. We're also going to get into coordinates, different types of coordinates, Boyer-Lindquist coordinates, and so forth. And this is going to be hopefully a really, really rich jumping point now into this area of GR. This is going to be fairly advanced stuff. And without further ado, if you like this kind of content, make sure to hit that like and subscribe button, and make sure to hit up my Patreon page if you want to see my notes on the stuff I'm going over. And with that being said, I will see you guys in the next video.